Hi there, welcome to this channel. Today we'll be talking about zoonotic spillover. This is part of a new series called Wildlife Disease Ecology or One Health. We're doing this in collaboration with the university and the Wildlife Conservation Society. And today I am very excited to have one of my co-authors here to talk about our paper that just came out in Nature. And to set the stage for this episode, it's me. Okay, so in this episode, we're going to talk about what drives spillover, which is when an infectious disease jumps from an animal host into humans. It's something that most people think about in terms of rare events, once in a century type events. But actually, spillover is happening all the time. Every year, there are spillover events that lead to thousands of cases of illness in humans. In some cases, those illnesses can be mild. In other cases, they can be severe. Some of these diseases are new, and others are ones we know quite a bit about already. For example, each year, thousands of people in the U.S. get sick with the disease Lyme disease, which is transmitted by ticks, and has been spilling over from white-footed mice into humans since at least the 1970s. And more recently, the world has been grappling with yet another novel coronavirus spilling over from bats into humans, so spillover is a constant threat. Now, spillover events don't necessarily result in pandemics, but they do have the potential to do so. And when thinking about preventing future pandemics, it's important to understand what drives spillover in the first place. And that is exactly what we set out to do in our recent paper in Nature, where we bring together insights from disease, ecology, conservation biology, and global change biology to try and answer the question of what factors drive spillover. So let's start by talking about the different types of spillover. Now, in our paper, we differentiate between two main types of spillover. The first is spillover from wildlife. So that could be something like SARS-CoV-2, spilling over from bats via an intermediate host species into humans. The second type of spillover that we consider in the paper is spillover from livestock. So that could include things like avian influenza spilling over from poultry into humans. Now, both of these types of spillover involve wildlife species, and that's why we call them zoonotic diseases. But in the case of the second type, livestock are an integral part of the system, and their presence is what is facilitating the spillover in the first place. Okay, so now let's talk about the factors that drive each of these types of spillover. We consider spillover from wildlife and livestock to be driven by three main factors: habitat disruption, wildlife trade, and livestock interfaces. Habitat disruption. Disruption is a driver of spillover when it increases the contact rate between wildlife and humans or livestock, or makes hosts more susceptible to infection, more infectious, or more likely to come into contact with the pathogen in the first place. So an example of this would be deforestation. Deforestation brings humans into closer contact with wildlife and creates conditions that favor spillover. That might happen because the forest habitat is being converted to agricultural land or to urban areas, or because of changes in fire regimes or the severity of droughts. When habitats are disrupted, animals lose their homes, and sometimes they end up in close proximity with humans and livestock, which creates opportunities for disease transmission. Another factor that can drive spillover is wildlife trade. Wildlife trade moves species across geographic areas, which can increase the likelihood that they come into contact with novel hosts and establish new diseases in those populations. These introductions may be intentional, such as when people move wildlife for the pet or fur trade or food, or they may be unintentional, such as when wildlife are transported as a stowaway in shipments of goods. Unintentional introduction of species is probably responsible for many of the invasive species that we have today, and has facilitated spread of diseases such as chytridiomyces, which is caused by the fungus Batrachochytrium dendrobatitis. This fungus has been moved around the world through the pet and meat trades, and is now thought to be responsible for declines in hundreds of amphibian species. The third factor that can drive spillover is livestock interfaces. Livestock interfaces occur when domestic animals come into contact with wildlife and are often associated with livestock production practices. For example, free ranging, which is when livestock are allowed to roam outside with no enclosure, can put them in close contact with wildlife and increase spillover risk. Another example is sharing water sources with wildlife, such as when livestock drink from the same rivers and streams that wildlife do, or sharing pastures, which is when livestock are raised in the same areas where wildlife live. And livestock interfaces also include practices associated with feeding livestock, such as when livestock eat crops grown in or near forests or are fed wild-caught rodents. Livestock interfaces are likely responsible for many of the diseases that jump from wildlife to livestock and then spill over to humans. Examples include diseases such as Ebola virus disease, which is thought to have spilled over from fruit bats to both chimpanzees and humans, and Nipah virus, which is thought to have jumped from bats to pigs and then to humans. All of these factors, habitat disruption, wildlife trade, and livestock interfaces, contribute to spillover events every day around the world. And while some of these events lead to widespread disease outbreaks, others don't. So why do some spillover events lead to epidemics while others don't? Well, in our paper, we identify three main factors that determine whether or not spillover leads to epidemics. First, the pathogen characteristics influence whether or not spillover leads to epidemics. For example, pathogens with long incubation periods, which are the time between infection and when an animal is infectious, have more opportunities for spread before they're detected. Pathogens that cause mild disease in wildlife also have the potential to spill over more easily because infected animals might never be detected. And pathogens that can be transmitted before an animal shows symptoms, such as through respiratory droplets, can spread quickly, especially if those droplets can remain infectious on surfaces for a long time. Second, host factors influence whether or not spillover leads to epidemics. Transmission from wildlife to humans is more likely to lead to epidemics when the host species that the disease jumps into has high population densities, short generation times, and is closely related to the original host. So, for example, MERS-CoV, which is a coronavirus related to SARS-CoV-2, jumped from bats to camels and then to humans. And the fact that humans and camels are more closely related to each other than camels are to bats made it more likely that the disease would jump from camels to humans. And the third factor that influences whether or not spillover leads to epidemics is human population density. If humans are densely packed together, then it's more likely that a disease introduced into that population will spread and become an epidemic. Now, we identified several key points in our paper, but one of the main ones is that spillover from livestock is more likely to cause epidemics than spillover from wildlife. That's mainly because livestock are more closely related to humans than most wildlife species are, and because livestock are often kept in high densities, which provides opportunities for spread. So for all of these reasons, spillover from livestock is probably responsible for the majority of deadly human diseases that have emerged in the last few decades. In our paper, we argue that addressing the three drivers of spillover from wildlife and livestock, and considering the three factors that influence the likelihood that spillover will become an epidemic, is crucial for preventing pandemics. And this requires a collaborative One Health approach that engages multiple sectors, including wildlife and livestock producers, policymakers, public health officials, ecologists, and conservation biologists. As we look ahead, it's clear that spillover events will continue to happen. But by understanding what drives spillover, we can work towards preventing the next pandemic. So thank you so much for listening.